All right. So in this lecture, we're going to talk about the concept of similarity. So similarity is something that relies on dimensionless parameters. So up until now, we've been figuring out how to derive dimensionless parameters, and we've often said that we'll have, after we're done deriving them, especially using the Buckingham pi theorem, we'll say we have some dimensionless parameter pi 1, and it could be a function of lots of other different dimensionless parameters, as many as we might have calculated. And it's really important that we think about this where we have this dependent pi variable and all these independent ones, because similarity is really going to depend on that. So the basic concept of similarity says if I have a situation like this where I have my dependent pi variable and it depends on a bunch of these independent ones, that if my independent pi variables between two situations are the same, then the dependent one should be the same. So typically what we'd say is we have a model, so typically this is used for modeling, all right, and our actual situation. So, all right, and so in a model, what we'd say is if we have, let's say we had a situation where we had pi 1 and it was a function of pi 2 and pi 3 for this particular problem, okay? What this means is that if we have pi 2 of our model and we have pi 3 of our model, and they equal pi 2 of the actual situation and pi 3 of the actual situation, then whatever pi 1 is of the model, it equals pi 1 of the actual situation. All right, and this is essentially saying that if the independent dimensionless groups are the same, if the independent pi groups of situation A and B are the same, then the dependent ones are as well. All right, now this seems a little confusing right now, but it's a really important tool. And it's a really important tool because it allows us to do modeling. That's why I used the term model and actual before. All right, so a quick example is that we often talk about the Reynolds number, and that's rho VD over mu. And we can talk about something called the drag coefficient, which a lot of you have mentioned in class before, which is force of drag over 1/2 rho v squared A, where A is a cross-sectional area. All right. So let's say we have a sphere, or a sphere that looks like this, and it's falling, okay, at some speed v, and we know it's in air, so there's rho, all right, and it has a diameter d, okay, and then the air has a viscosity mu, all right, and as it's falling, we were able to measure its drag force, okay, so we could measure the drag force. So let's say, for instance, we put this in a wind tunnel. Here's our little wind tunnel picture. Okay, and we put the ball here, all right, and so let me write this here, and we have it attached to like basically a spring, so we can use the spring's displacement to measure our drag force, right? And so we have, again, here's our velocity, and we'd have the viscosity and density of air and the diameter of the ball. Let's call this our model, all right? And we go to our model and we say, all right, for our model, the Reynolds number equals rho of the model times v of the model times d of the model, put a model there, over the viscosity of the model. And we measured a drag coefficient using that spring there, okay? All right, so you've done this for the model, and you might say, well, why does this matter? Well, let's say there's a comet and it's going to crash into Earth, and the size of the comet's huge, right? So now we have this comet. I'll draw a little picture of the Earth here. Here's the Earth. All right, there's the Earth, and there's South America. All right. And now we have this huge comet, and it's that's really big. I'll draw it a little smaller. We have this huge comet that's going to hit the Earth, and we want to go, what force is it going to hit the Earth with, or what's the drag force on the comet? Will it slow down before it hits the Earth? Well, there's no way we could do an experiment, right? This comet's far too big. But let's say we figure out, we calculate the Reynolds number of this comet, and it equals the Reynolds number from our model. That means the drag coefficient from our model is the drag coefficient, all right, of our comet. And so if we wanted to know, say, the drag on the comet, we could say, well, that's CDA times 1/2 rho of actual V actual squared A. And since CDA and CDM are the same, right, we can now calculate this value that we actually wanted, right? And that's how modeling works, the basic idea. Now, what's important when modeling is that typically when we think about modeling, we'll think about it in 3 ways, similar to the variables we've talked about in the Buckingham-Pi theorem, which is there's geometric similarity, kinematic similarity, and dynamic similarity. Geometric is exactly what it sounds. This means the geometry is similar. So this is like saying something is 1/10 scale, right? That means all the geometry is 1/10 scale. For our purposes, it would mean things like if we had L over D, H over D, where we had these purely geometric dimensionless groups, that they would all be the same between 2 situations, all right? Kinematic similarity means timescale similarity. So again, for us, that would mean things like velocities, so dimensionless groups with velocity. So if we had a V over V0, or if we had a T, some time scale times some frequency time scale, whatever that. So any particular dimensionless group that dealt with the kinematics, those would be similar. All right. And then dynamic similarity means that all the dimensionless groups are similar, and this includes forces. All right. Now, if you want to truly use a model, right, then dimensionless similarity or dynamic similarity here is the best one, because that includes all the forces. If things are only kinematically similar, then you can only compare kinematics, and if they're geometrically similar, they're only geometrically similar, right? They only look the same shape, okay? So that's the thing here. All right. So the real use of this idea of similarity is that we can take results from one area, all right, and apply them to another, and we can then use the dimensionless groups to calculate dimensional variables that we want, like I showed you in that drag, all right, example. For our purposes in this class, when you think about this problem and you're thinking about these 3 ideas of geometric, kinematic, and dynamic similarity, you can think about particular variables in our problem. But for geometric similarity, just think about things being like, if we say something is 1/10 scale. For kinematics, we would be thinking about velocities, and for dynamics, we're thinking about everything. And hopefully, whenever we really want to use this problem, like I said, we really want dynamic similarity, this one, and that's what we're going to assume we have when we do any sort of modeling situation. And what that means is really what you're assuming is if you've gotten all the right dimensionless groups. So if you try and do something with dynamic similarity and it turns out your model's not well predicting your real situation, it probably means you're missing some dimensionless groups. But in purposes of this class, if I say the thing is dynamically similar, then that's all you need to worry about. If you do the Buckingham-Pi theorem and you've got a bunch of dimensionless groups on your own, then for dynamic similarity, you just have to use all of them, and then you might find out some of them are good or some of them are bad. All right, that's it. That's all there is to know about similarity.